Hi, I'm Mark Barsamian. In this video, I'll be discussing relations on sets. More specifically, I'll be giving the definition of a relation on a set, and then discussing ways of illustrating relations on finite sets using tables, arrow diagrams, and what are called directed graphs. There's a typo there that should say. I'll also be discussing inverse relations and unions and intersections of relations. All this material is from section 8.1 in the book. The corresponding homework is this collection of 6 exercises from section 8.1. We'll be using some old stuff from way back in chapter 1, the definition of ordered pairs. A comma B in parentheses is an ordered pair. The definition of the Cartesian product of sets. So that's going to be an important one today. Remember that this symbol, capital A subscript 1 cross capital A subscript 2, where capital A subscript 1 and capital A subscript 2 are sets, that symbol denotes what's called the Cartesian product of those two sets. And what that means is the set of all ordered pairs. So the set of all ordered pairs of the form A1 comma A2, where little a1 is in set capital A1 and little a2 is in set capital A2. And then we'll be returning to the definition of relation from way back in section 1.3. Remember that a relation R from a set A to a set B is just simply a subset of the Cartesian product A comma B. And so it's just a collection of ordered pairs. Now, relations get an additional layer of terminology and notation. We say that X is related to Y by R, or we write this symbol, XRY, to mean that this ordered pair is in that set that is the relation. Now, for the relation R from A to B, the set A is called the domain of the relation, the set B is called the codomain of the relation. And again, this symbol XRY means that that ordered pair X comma Y is in the set that is the relation. And this symbol X slash RY means that that ordered pair is not in the relation. This first one is spoken X is related to Y. This second one is spoken X is not related to Y. Now in the current section, 8.1, we'll be discussing relations on a set. A relation on a set A is simply a relation from A to A. Let's start with an example. Let A be this set, and define a relation on set A by saying this. XRY means that X and Y have a common prime factor. So we just have some questions about expressions involving that symbol. So this first question is spoken, is 2 related to 6? So that means, is it true that 2 and 6 have a common prime factor? So 2 and 6 have a common prime factor of 2, so they are related. So this symbol, 2R6, is true. Is 6 related to 2? Yes. For the same reason as the previous, 6 and 2 have a common prime factor of 2. Is 5 related to 5? Yes, because 5 and 5 both have a prime factor of 5. And finally, is 2 related to 5? Well, no, because 2 and 5 don't have any common prime factors. Now, describe R explicitly by listing its elements in set roster notation. Remember that what that means. You just use set brackets and show all the elements of the set. So there is the set R, that is the relation R, which is a subset of A cross A. Now notice that this set roster notation is very thorough, but it's really tedious to write and tedious to read. I mean, you can't really expect someone to look at this and not go to sleep. So that brings us to the idea of illustrating relations. There are going to be lots of different ways of illustrating different kinds of relations, and it's a good idea to be familiar with as many different ways of illustrating as possible, and for a particular relation, be able to illustrate it in more than one way. One way to illustrate a relation on a finite set is to use a table. So question B is to illustrate the relation R that we've been talking about using a table. Well, let's go back and look at that relation. Now remember that relation R is a relation on set A. 2, 3, 4, 5, 6, 7, 8 are the elements of A. I'll make a table in the following way. So there's a table showing the elements of A listed as the entries in the first cells of each row, and listed again as the first cell of each column. Now, what the cells in this table are going to represent are the following ordered pairs. So the element on the left of an ordered pair will be green, and the element on the right will be red. And so let's go back up and look at our set roster. For this element in the relation, 2, 8, that's going to be a green 2 and a red 8. That will be listed here. So I'm going to go ahead and just show all those pairs by putting X's in all the cells that correspond to those pairs. 2 is related to 2, 2 is related to 4, 2 is related to 6, and so forth. Now, notice I've made a mistake in my set roster. I forgot to put an X there. 3 is related to 6, and I forgot to put an X here. 6 is related to 3. Let's go back up. So you can see that the illustration using a table is maybe a little bit slower to construct, but it's a lot faster to read and make sense of. For instance, you can see these prime numbers, 5 and 7, that are only related to themselves. The prime number 3 is related to itself, but also related to 6. I happen to put another number in that set that has a common prime factor with 3. Another way to illustrate a relation on a finite set is to use an arrow diagram. And so the way that you diagram a relation with an arrow diagram is you have the domain set A, you illustrate that as points in one region, and the codomain set B you illustrate with another region, and for every pair A is related to B or X is related to Y, you draw an arrow from X to Y. So for question C, let's illustrate our relation R that we've been talking about in example 1 using an arrow diagram. So that arrow that I just drew there, for instance, represents the pair 2, 6. The number on the left we're thinking of as a green number, and the number on the right and the pair we're thinking of as a red number. I'm going to get rid of those that ordered pair though, because I want to leave room for the arrows. So we're going to have an arrow for each of the ordered pairs that we listed earlier. So there's our arrow diagram for the relation R. Notice it's actually kind of cluttered. That's okay. The idea is that we want to practice doing as many different kinds of illustrations as we can, so that we will begin to get a sense of which kind of illustration will be most useful in different kinds of situations. And the only way to get that sense is to just draw lots of examples of illustrations. Another kind of illustration that you can use for illustrating finite sets is what's called a directed graph. So you can modify the arrow diagram so that instead of representing the set A as 2 separate sets, notice in our previous illustration, this was set A, and this was also set A. In a directed graph, you represent the set A only once, and you draw an arrow from each point of A to each related point, and you draw with an ordinary arrow. So on a directed graph, there is an arrow from an x to a y every time there's an ordered pair, x comma y. And if a point is related to itself, a loop is drawn that extends outward from that point and goes right back to it. So as an example, let's illustrate our relation R using a directed graph. Now, when making a directed graph, it's often a good way to start by just putting the points around a circle. Now notice that we know that every number is related to itself because every number in this set shares a prime factor with itself. So each of these numbers gets a loop. And then there are the arrows that we know about from one number to some other number. So 2 is related to 4, so there's an arrow from 2 to 4, and from 2 to 6, and from 2 to 8, and so forth. 3, in addition to being related to itself, 3 is related to 6. Now remember that 4 is related to 2, and to 6, and to 8, and so forth. So there's our directed graph. Now, one thing that you will notice is that, of course, this is very cluttered, but also that there are a lot of things that are kind of crashing into each other that could maybe be rearranged so that they don't crash into each other. So for instance, we could move the number 3 somewhere else so we wouldn't have these arrows crashing into quite so many arrows. So having made this first illustration, let's just make another one. I'll do that on the next page. So there's a second version of a directed graph for relation R. Notice there aren't quite so many crossings in this version. Let's go on. Example 2. Let A be this set. I should have set brackets around it. 0, 1, 3, 4, 5, 6. Define a relation V on A by saying this, that x vy means 5 divides x squared minus y squared. So question A is to describe V explicitly by listing its elements in set roster notation. Well, this will just be kind of tedious, but let's just go through it. So notice right away that 0 squared minus 0 squared is the number 0, and I can write that 0 equals 5 times 0. So 5 does divide 0 squared minus 0 squared. So we have the ordered pair 0, 0 in this set. Of course, that's going to work that way for every ordered pair where the number appears twice. So so all of these ordered pairs will be in the set as well. Here I should have said, so we've got a bunch of ordered pairs that are in the set V. Now notice a couple of obvious things. If I take 5 squared minus 0 squared, I get 5 squared. And 5 does divide 5 squared. And 5 also divides 0 squared minus 5 squared. So the pair 5, 0 and the pair 0, 5 are also in the relation. What about the number 1? Well, 1 is related to quite to a number of points here. Notice that 4 squared minus 1 squared is 16 minus 1. That's 15. And 5 does divide 15. And 5 divides negative 15. So from those two expressions, we can see that there are 2 more pairs we can put in our relation. I should say that the ordered pairs are elements of the relation V. The relation is called V, not R. Now what about the number 3? What is it related to? Well, let's see. I don't think it's related to anything. We've already seen that 4 is related to 1 because 16 minus 1 is 15. Is 4 related to anything else? Yes, 4 is related to 6 because watch. 6 squared minus 4 squared, that's 36 minus 16. That's going to be 20. 5 does divide 20. And similarly, 5 divides negative 20. So those pairs are in V. 4 is not related to any other numbers besides 1 and 6. We see that 5 is related to 0, and of course 5 is related to itself, so we've already got those. What about 6? We've seen that 6 is related to 4, and 4 is related to 6, and we've seen that 6 is related to itself. 36 minus any other, 36 minus 1 is 35. So we can write this. 5 divides 6 squared minus 1 squared. That is 5 divides 35. And 5 divides negative 35. So that gives us 2 more ordered pairs. So in set roster notation, we would write this. So there's my list of all of the elements of set V. Notice that I give it the name. V is that set. V is a subset of the Cartesian product. All right, question B. We're supposed to illustrate V using a table. Let's do the same thing with green and red numbers. So the numbers are 0, 1, 3, 4, 5, 6. So let's go back up and look again, double check we've done everything right. So 0, 1, 3, 4, 5, 6 are our elements. So that's set A, listed twice in our table. And the cells of this table are going to represent pairs of this form. All right, let's fill in our table. Now remember that every element was related to itself. And remember that 0 was related to 5. And remember that 1 was related to itself and to 4 and to 6. 3 was only related to itself. 4 is related to 1 and to itself and to 6. 5 is related to itself and also related to 0. 6 is related to, let's see, 1 and 4. So there's our illustration of the relation V using a table. So the X's represent the ordered pairs that are in set V. Let's illustrate V using an arrow diagram. Remember that every number was related to itself. I should have put that in first. And 0 is also related to 5. And 1 is also related to 4 and to 6. What other pairs are we missing? 3 is only related to itself. 4 is related to 1 and to itself and to 6. 5 is related to itself and also related to 0. And 6 is related to itself and related to 1 and to 4. So there's an arrow diagram. Now let's illustrate V using a directed graph. Every element is related to itself, so each one of these gets a loop. 0 and 5 are related, and 1, 4, and 6 are related in both directions. Now look, we also could clean this up quite a bit by moving stuff around. Look, this pair of numbers, 0 and 5, aren't related to any of the other numbers, so we might as well list them off to the side. So there is a directed graph that's much easier to read. So the point of these illustration styles is that different ones are useful in different situations, and it's very helpful to think about ways of making a particular illustration clearer. Let's go on. Now let's talk about some relations on sets that are described abstractly rather than explicitly. So let's let X be this set ABC. Now remember that this symbol, script P parentheses capital X, denotes the power set of capital X, which is the set of all subsets of X. So define a relation called capital S on the power set of X by saying that ASB means that set A has the same number of elements as set B. So we're going to be taking subsets of X and we're going to be putting them on either side of this letter S. So consider this symbol. The thing on the left is a subset of set X. The thing on the right is a subset of set X. So those are elements of the power set. So is this symbol true? Is the set containing C related to the set containing B? Well, that would mean that this set has the same number of elements as that set. So yes, they are related because they both have one element. But for this next question, is this set related to this set? That is, do they have the same number of elements? The answer is no. The set on the left has one element, the set on the right has two elements. What about this question? Is XSX true? That means, is it true that X has the same number of elements as itself? Well, yes, X has 3 elements, and X has 3 elements there too. So what about this last question? Is that true? Phi S phi. Well, remember that phi is the empty set. So the number of elements in phi is 0. So there's the symbol phi, which denotes the empty set, and there's the number 0. That's the number of elements in that set. And so this is true because 0 equals 0. Okay, let's go on. Now I want to talk about inverse relations. If R is a relation from A to B, define the inverse relation, denoted R superscript -1, as a relation from B to A, as follows. So R inverse is going to be a subset of B cross A. So R inverse is a relation from B to A, so that means it's a subset of B cross A. So we have to tell what ordered pairs are in that relation. Now each ordered pair will be an ordered pair of the form y comma x, where y is in B and x is in A. Now this equation tells us, or this set description tells us exactly which of those pairs are in the set R superscript -1. It's all the pairs y comma x such that x comma y is in R. So in other words, you take the set roster for all of the ordered pairs that are in set R, and you interchange the x, y coordinates, and you get a new set roster. That's all the elements of R inverse. So for example, let A be this set, 3, 4, 5, and let B be this set, 4, 5, 6. And let R be the less than relation. That is, XRY means X is less than Y. So the question A says, to state explicitly which ordered pairs are in R and which ordered pairs are in R inverse. Now I'm going to do this in colors. I'm going to denote set A in green. And I'm going to denote set B in red. So here are my ordered pairs in set R. So there are my ordered pairs in set R. So this set R inverse, or the relation R inverse, is going to be this set of pairs. So there we go. We just simply interchanged the roles of x and y in all the ordered pairs. Let's illustrate R and R inverse using tables. Well, here's the illustration of R. So there are the two tables. Notice that the entries for this table are obtained by taking the entries in this table and flipping them across the main diagonal. Let's go on. Let's illustrate R and R inverse using arrow diagrams. Okay, for R, we're going to have a map from set A to set B. A is 3, 4, 5 in green, and B is 4, 5, 6 in red. So there is my relation R. Now, to illustrate relation R inverse, I should put the elements of B on the left. Now, we can see that there is an arrow from 4 to 3 because in the original diagram, there's an arrow from 3 to 4. Now, there are all these arrows that emanate from 3, from the green 3 to the red 4, the red 5, the red 6. So that means that there are going to be arrows going back from those red numbers to the green 3. Now look at these two arrows emanating from the green 4, going to the red 5 and the red 6. Well, that means that from the red 5 and red 6, there are going to be arrows going back to 4, the green 4, in the arrow diagram for R inverse. Now look at this arrow that goes from the green 5 to the red 6. For the inverse relation, there will be an arrow from the red 6 back to the green 5. So there is the arrow diagram for R inverse. Now notice that this would have been maybe faster to get by just simply reversing the directions of all these arrows. But we really want to have the arrows going from left to right. Let's go on. Now I want to talk about unions and intersections of relations. Remember that relations are just sets, so we can talk about their unions and intersections. So let A be this green set whose elements are 2 and 4, and let B be this red set whose elements are 6, 8, and 10. Define two relations from A to B. Relation R is defined by saying that XRY means that X divides Y. Relation S is defined by saying that XRY means that Y minus 4 equals X. Or another way of saying that would be that Y equals 4 plus X. So we have to state explicitly what ordered pairs are in all of these sets. Okay, let's just get busy. That symbol, A cross B, is the set of all ordered pairs, where the left element is in set A and the right element is in set B. Well, notice there are 2 elements in A and 3 elements in B, so there are going to be a total of 6 elements in the cross product. So I'm going to make 6 ordered pairs. And every ordered pair is going to have a green number on the left and a red number on the right. So there are my ordered pairs for the Cartesian product. Now, what is the relation R as a set? R is going to be all the ordered pairs that have an X and a Y such that X divides Y. Well, let's see. 2 divides all three of these numbers. So there are going to be three pairs that have a 2 on the left. 4 only divides that number, so there's only going to be one pair with a 4 on the left. So notice every ordered pair that's in set R is an element of A cross B. So this set R is a subset of A cross B. Capital R is a relation. Now let's make a set roster listing of set S. S is the set of all ordered pairs x and y such that y minus 4 equals x. Or you could say that y equals x plus 4. Well, notice that 6 equals 2 plus 4, and 8 equals 4 plus 4. So there are going to be only two ordered pairs in set S. The ordered pair 2, 6 and the ordered pair 4, 8. So that's the set S. Again, it's a subset of the Cartesian product A cross B. Now finally, what's new is this. Take the union of those two relations. R union S is this set union this set. Well, notice that every element in set S is already in set R. Finally, we need to find R intersection S. What are all the ordered pairs that are both in R and in S? Well, notice that, again, every element of S is in R. So therefore, R intersect S is just S. That's the end of that example, and that's the end of the video. Thank you.